All right, so let's solve this problem. The angular velocity of a rotating rigid body increases from 500 to 1500 revolutions per minute in 120 seconds. Okay, so you see this is a different unit of time, that's a different unit of time. So we have to have the same unit of time. Okay? So either we'll convert this to seconds or convert that to minutes. Okay? So, and we generally want to have seconds as the unit, so that's what we'll do. Okay? What is the angular acceleration of the body? Okay. And so here's a picture. So the axis is coming out and it's rotating like that. What is the direction of the velocity for this guy? How do you figure out the direction? You use your right hand, point your fingers in the direction of rotation, and your thumb points in the direction of the velocity. Okay? The velocity direction is along the axis. Okay? That's the convention. You can convince everybody in the world and use the convention, use your left hand. Okay? It's just like calling one set of people boys and the other set of people girls. Okay? You can switch them around if you want. It doesn't matter. Okay. So, all right, so initial angular velocity is 500 revolutions per minute. And what I'll do is I'll convert it into radians per second if you want. Okay. So 1 revolution is 2 pi radians, and 1 minute is 60 seconds. Okay. So we've converted the velocity into radians per second. Okay, similarly, the final velocity will be, well, that's 3 times that, so 156, 7.2 radians per second. Okay. And you saw that angular acceleration is omega final minus omega initial. By t. So 157.2. So assuming constant angular acceleration, this is where I got that from. For constant angular acceleration, final angular velocity is initial angular velocity plus alpha times t. Bring that there, divide by t, you get alpha. Okay. Minus 52.4 divided by 120 seconds. Okay, so what does this mean? 1 radian is about 60 degrees. So 0.9 radians, that's about 54 degrees. 54 degrees per second per second. So the angular velocity is increasing by 54 degrees per second every second. Okay? So that's what that number means. Through what angle does it rotate in this 120 seconds? So its been initial velocity was 500 revolutions per minute, and then it's speeding up to 1500 revolutions per minute. And then 120 seconds, what was the angle through which it rotated? So you can use this formula, theta final minus theta initial. This is the angle through which it rotated, is omega initial times t plus 1/2 alpha times t squared. Okay. So this, and we'll do the radians per second, 52.4 radians per second times 120 seconds plus 1/2. Alpha was 0.87. Okay. So you will get this in radians. Okay, so roughly 12,500 radians. And remember, 60 radians is 1 revolution, so 120 20 radians would be 6, what did I say? 60 degrees is 1 radian. 360 degrees is 1 revolution. Okay. 120 would be 1/3 of that, 1/3 revolution. So 1/3 of 1,000, roughly 300 radians, 300 revolutions. Okay. 350 revolutions, roughly in that ballpark. Okay. That's what that means. Okay, in this problem, a flywheel slows down from 600 to 400 revolutions per minute. Okay, so here's a flywheel, and again, there's the axis of rotation. There's the initial velocity. Initial velocity is pointing in this direction, and alpha is pointing in the opposite direction. Okay, it's slowing down. So a flywheel slows from 600 to 400 revolutions per minute while rotating through 40 revolutions. Okay, what is the angular acceleration of the flywheel? Okay, so what we can do is we can calculate in revolutions per minute square. So I'll do it in different units just so you. Okay, so what is it we're calculating? What is the angular acceleration? Okay. So we can use this formula. Okay, so this was the angular displacement was 40 revolutions. We have the final angular velocity. We have the initial angular velocity, so you can calculate that. Okay. So alpha is okay, and so alpha is equal to 400 square minus 600 square divided by 2.40. This was revolution square by minute square divided by revolution. So alpha will come out in revolutions per minute square. Okay. Okay, so that's the angular acceleration. The negative sign just telling you that the acceleration is pointing in the opposite direction of the initial velocity, which was taken to be positive. Okay. How much time elapses? Omega final equal to omega initial plus alpha times t. T is omega final minus omega initial divided by alpha, 600, no, 400 revolutions per minute minus 600 divided by minus 2000 revolutions per minute squared. So what you get is minutes at the top. Okay. And to convert that to seconds, multiplied by, okay, so 5 seconds. In 5 seconds, it's rotated through 40 degrees, 40 revolutions. Okay. A rod of length 20 centimeters has 2 beads attached to its ends. The rod with beads starts rotating from rest. If the beads are to have a tangential speed of 20 meters per second in 7 seconds, what is the angular acceleration of the rod to achieve this? Okay. So here's the rod, it's rotating about that axis. There are the 2 beads going in circles. Okay. All right. The length of the rod is 20 centimeters, so this is 10 centimeters. Okay. So the radius is, this is 10 centimeters. Okay. And you're going at 20 meters per second after 7 seconds. Okay. So for that linear velocity, r omega, the angular velocity is v over r, which is 20 meters per second, divided by r is 0.1 meters, equal to 200. What are the units?
Radians.
Yeah, so the meters cancel. All the units is 1 over second. Radians is a free label. It's a dimensional. Okay. So very good. Radians per second. Good. Remember, whenever you're using formulas that involve linear and angular quantities, those guys are in radians per second. Okay. The angular quantities are in radians. So you have to be careful about that. Okay. All right. So this is the final angular velocity you have to achieve to be going at that speed. You started off at rest. So omega final is omega initial plus alpha t. Okay, so what is it that what is the angular acceleration? Alpha is omega minus omega initial divided by t. So 200 radians minus 0 over 7 seconds. Okay, so this was the angular acceleration you needed. Okay. All right. So this problem says a man stands on a merry-go-round that is rotating at 2.5 radians per second. If the coefficient of static friction between the man's shoes and the merry-go-round is mu s is 0.5, how far from the axis of rotation can he stand without sliding? Okay. So here's a top view. There's the merry-go-round, and it's spinning about this axis. Okay, so it's spinning about that axis. All right, so if you're standing here and going at that speed, to make you go in a circle, you need a centripetal force. What is the centripetal force you need? mv squared by r. Now, v is given by r omega. Omega is the angular velocity. So the centripetal force is v is r omega, so r omega squared divided by r, it's equal to mr omega squared. So you see, the further from the axis you are, the greater the centripetal force you need to keep you going in a circle. And the only thing that's providing the centripetal force is the static friction force. Okay? Your shoes are the only thing that are in touch with the merry-go-round. Okay? So this is, and the static friction force has a maximum value. So the maximum static friction force, m omega squared r max. That's the furthest you can stand. All right, so if you're standing at the center of the merry-go-round, how fast can it spin?
However fast it wants.
As fast as it wants, because you don't need any centripetal force. You're not going to fly away. Okay? So, in fact, so this is what happens. In fact, if there's dirt on your car wheels, the faster your car wheel rotates, eventually all that dirt will fly away because it's not sticky enough. Okay. So if your car's tires don't get clean, that means you're not driving fast enough. Yeah. All right, what is Fs max? It's mu s times mg. Okay, since the mass canceled, everybody wearing those same shoes should be able to stand at the same distance. Okay, that would be the maximum distance for everybody. And mu s is 0.5. G is, what is it? How far from the axis? Okay. 9.8 meters per second square. And that will come out in meters. Okay, so roughly 0.8 meters away. Okay. So if you stand any further, your shoes are not sticky enough and you would fly. You'd fly away. You would slip away. Okay? Okay, a system of point particles is shown in the following figure. Each particle has a mass 0.3 kg and they lie in the same plane. So this is in a plane. So What is the moment of inertia of the system about the given axis? Okay, we are assuming that the axis is coming out of the plane, and these guys are all in a plane. Okay, so the axis is coming out of this point, and it's perpendicular to the plane. If the system rotates at 5 revolutions per second, what is its rotational kinetic energy? Okay, so moment of inertia is given by MI/RI squared. Okay, so here are these are point particles. There is the distance of each of those guys. So the mass is common, MRI squared in our case. Okay, so that's 0.3 kgs, and the summation of 0.2 meters squared plus 0.4 meters squared plus 0.6 meters squared. So the moment of inertia is okay, 0.3 into 0.04 plus 0.16 plus 0.36 kg meter squared. Those are the units. Okay, so that's 0.4, 0.56, so 0.3 times 0.56 kg meter squared. So 1 point, no, that's 0.05, yeah, 0.15. Right? So there's the moment of inertia, 0.1. 56 times 3 is 168, and there's 3 decimal spots. Okay. All right. If the system is rotating at angular velocity is 5 revolutions per second, okay, we have to convert that to radians per second. 5 into 2 pi radians per second. And kinetic energy is 1/2 I omega squared. So 83 joules. Okay. All right, so this says a system consists of a disk of mass 2 kg, so that's a disk, and radius 50 centimeters, upon which is mounted an annular cylinder. So here's a cylinder sitting on top of the disk. So this is a top view, and it's going to rotate about that axis. We're going to calculate the moment of inertia about an axis perpendicular to the plane and coming out of that point. Okay? The system rotates about an axis through the center of the disk and annular cylinder at 10 revolutions per minute. So the angular velocity is that. What is the moment of inertia of the system? Okay. So the moment of inertia, just like the mass of a system is, you sum the mass of individual particles, just like that. You add up the moment of inertia of various objects. Of course, you have to be calculating about the same axis. You can't calculate the moment of inertia of this object about this axis and calculate the moment of inertia of that object about some other axis. You're calculating about the same axis, okay, about this axis, okay, the axis about which it's rotating. Okay, so the total moment of inertia is the moment of inertia of the disk plus the moment of inertia of the ring. You guys can again look up the formula in the tables. It's mass of the disk times radius of the disk square plus 1/2 mass of the ring times inner radius square plus outer radius square. Okay, now if the inner radius becomes 0, what does this ring become?
Just a cylinder?
It just becomes a disk.
Oh.
If this becomes 0, that formula reduces to that formula. Okay. If the inner radius is equal to the outer radius, that's just a ring, and all the mass is at r square, this becomes 2r out square, and that cancels that. Okay, so that has the right limits. Okay. All right, so let's calculate the moment of inertia. 1/2, 2 kgs is the mass, and 0.5 meters is, mass of the ring is 1 kgs. Inner radius is 0.2 kg meter square. Okay. So the moment of inertia is, so this cancels, that's 0.25 plus, that's 0.5, that's 0.04, 0.09, 0.13, half of that is 0.065. Okay. So there's the moment of inertia of this combined object. Okay. The system rotates about an axis at 10 revolutions per second. What is the moment? What is the rotational kinetic energy? Okay, so that was part A. And part B is and omega is, you have to convert that to radians per second, 20 pi radians per second. Okay, and now you can plug that in there. All right, so in this problem, they say calculate the torque about the z-axis. So here's the x, y, and which way is the z-axis? Is it coming out of the paper or going into the paper? So here's how you tell, okay? Use your right hand, turn your fingers from the x-axis to the y-axis, and your thumb points in the direction of the z-axis, okay? So if you turn from here to there, the z-axis comes out of the paper. Okay? That is a right-handed coordinate system. Okay? If you wanted a left-handed coordinate system, you use your left hand, point from x to y-axis, and your thumb points in the direction of Z. So for a left-handed coordinate system, Z would go into the sheet. Okay. We've all agreed in the world. You guys have signed the paper. We'll all use the right-handed coordinate system. Okay. All right. So Z comes out of the sheet. Okay. Calculate the torque about the Z-axis. This is out of the page at the origin in the following figure. Okay. What would be the torque of this guy? He's going through the axis, so his moment arm is 0. This guy will have no torque. This guy's, there's the component, so this guy can be broken up into a force like that and a force like this. This guy is going through the axis, he will have no torque. Only this guy will have torque. That's the moment arm for him. Okay. Now this is 90 degrees, so the moment arm for him is that. The moment arm, this guy can be broken up into a force like that and that. And again, this will have no torque. This component will have a torque. Okay. All right, this guy is F2 cosine 30. This guy is F4 cosine 20. Okay, and again, if a force tends to, so imagine an object on which these forces are acting. So there's a disk. What is this force trying to do? It's trying to rotate it counterclockwise. This force is trying to rotate it clockwise. This guy is trying to rotate the object clockwise. So counterclockwise rotations, remember, point your fingers in the direction of the rotation using your right hand, and your thumb points in the direction of the vector. Okay, so those torques will be positive along the z-axis. Torques will be pointing along the z-axis. So that this will give you a positive torque. This will give you a negative torque. Okay. Again, the easiest thing to remember is counterclockwise rotations are positive, and clockwise rotations are negative. Okay. All right. The net torque is the torque. So torques can either point, they can only point in the direction of the z-axis, so we don't need to write vectors. The signs tell you the direction of the vector. Yeah. Torque 1 plus torque 2 plus torque 3 plus torque 4. Okay, force 1 is making it rotate clockwise. That'll be a negative torque. So there's the magnitude of the force, and there is the moment arm. So F1 is negative 3 newtons and 3 meters. F2 is a counterclockwise torque, so that'll be a positive torque, plus F2 cosine theta, 2 newtons times cosine 30, because only this component is producing a torque, this component is not producing a torque. Okay. Times the moment arm is 2 meters. The torque for this force is 0 because the moment arm is 0. It's going through the axis. So that is 0. And then for the fourth force, again, this component is not producing a torque. This component is producing a torque, but this is a clockwise torque, so it's negative. And that is F4 is 1.8 newtons cosine 20 times 2 meters. And that's the net torque. Okay. So let's calculate this. And the units are, for torques, Newton meter. And if you guys refer to your notes before, the units for energy were Newton meters and they were called joules. But for torque, we won't call it joules. We'll write it as Newton meters. Okay. So that tells you what you're talking about. Okay, even those, depending on the context, this was called a joule before, but that was when you were talking about energy. So when you're talking about torques, you'll just leave it like that, the units. Okay. This is minus 9, and I'm sorry, 0.85. No, that doesn't.
It's 9.85.
No, that's 4 times cosine 30. $3.46 minus okay. So that is 0.08, and so minus 8.92. Okay, the torque is negative, so all those three forces combined will rotate the object clockwise. That's what, okay? So if it was at rest, it will give the object an acceleration in the negative, in the clockwise direction. So that's what that means. A seesaw has length 10 meters and uniform mass 10 kg and is resting at an angle 30 degrees. Okay, so if it has uniform mass, what does that mean? What are they telling you? What they're telling you is the center of mass is at the geometric center. Okay? So, and if it's leaning over like that, where's the center of mass? The center of mass is somewhere to the right. Okay? That's the center of mass. It's resting at an angle 30 degrees with respect to the pivot is located at and uniform mass 10 kg and is resting with respect to the ground. The pivot is located at 6 meters. Oh, okay, so this is at 6 meters. Okay. So this is 4 meters. And this is 6 meters. So this is 1 meter. Okay. All right. What magnitude of force needs to be applied perpendicular to the seesaw at the raised end so as to allow the seesaw to barely start moving? Okay. So what you want to find is what kind of force do you need to apply there to start the pivot, the seesaw moving? Okay. So if you apply a force like this, it will, about the pivot point, this will apply a counterclockwise torque. It will try to rotate it this way. What is stopping it? The weight of this, the weight mg is trying to rotate this clockwise. So in equilibrium, this counterclockwise torque is being balanced by this clockwise torque. Okay? All right, for this clockwise torque, the moment arm is this distance. Okay, and that distance is, so this is 1 meter, this angle is 30 degrees, that angle is 30 degrees. Okay, so the moment arm is 1 meter cosine 30. Okay, so for this guy, the moment arm is 4 meters. Okay, so F times 4 meters. So again, the net torque is I times alpha, and it's barely moving. Okay, so it's in equilibrium essentially. Alpha is 0, so the net torque is 0. And F times 4 meters, that's a positive torque, minus mg times 1 cosine 30 should be equal to 0. Everybody, you guys understand that this guy is the moment arm for this force, and this is 1 meter, and that angle is 30 degrees, which is opposite angles are equal, okay? And so it's 1 cosine 30. So the force is mg cosine 30 divided by 4. Okay. So the force you have to apply is 22% the weight of the board, okay, to lift it up. Okay, let me ask you this, okay, and you guys probably will intuitively answer this correctly, okay. So if I move this closer there, so if this becomes 4.5 meters, this distance, will the force you need to apply increase or decrease? Decrease, very good, okay. All right, so this is the last problem. Suppose when the Earth was created, it was not rotating. However, after the application of a uniform torque, after 6 days, it was rotating at 1 revolution per day. Okay, so form the Earth at rest, and then you give it a spin. Okay. Actually, the Earth back when it was first formed, it was spinning faster. It was spinning at about once every 9 hours or so. So now your day is 24-hour long. Okay. What was the angular acceleration during the 6 days? Okay. So So it was initially created at rest, and after 6 days, you gave it a final angular velocity of 1 revolution per day. Okay? So we're going to calculate the angular acceleration. Okay, so we want to convert all of these guys. Final is 1 revolution per day. We'll convert it into seconds, okay, radians per second and so on. So this is 2 pi radians, and 1 day is 24 hours. Each hour is 3,600 seconds. So alpha is 7.3 into 10 to the minus 5. Initial angular velocity was that. And we did this over 6 days. So this was in radians per second. And we want to convert that time into 6 days. Each day is 24 hours, that many seconds. Okay? So that'll be the angular acceleration. So there's the angular acceleration. Okay. By the way, so iOS 18, the calculator has become really nice on these phones. Have you guys checked out the new calculator? It's a vast improvement. All right. Now, what torque was applied to Earth during this period? So you saw that torque is I times alpha, and we'll consider the Earth to be like a bowling ball, a solid sphere of uniform density. Under those circumstances, it's mr squared. M is the mass of the Earth times that. Okay, so this is the torque you need to apply. And 2/5 mass of the Earth is 6 times 10 to the 24 kgs. Radius of the Earth is 6,400 kilometers. So 6.4 into 10 to the power 6 meters times 1.4 into 10 minus 10 radians per second squared. All right. Generally, it's a good thing to do, take care of powers of 10 in your head. Okay, that's 24 plus 12 is 36 minus 10 is 26. Okay, so the torque is 10 to the 26. What are the units for torque? Newton meters. Very good. Okay, so the rest of the stuff is 2/5 into 6 into 6.4 square into 1.4. Okay, so that's the torque you would have to apply to get the Earth to spin at 1 revolution a day from rest in 6 days. Okay. Now, part C says, what force tangent to Earth at its equator would produce this torque? So what they're asking you is the following. So let's say this is the Earth. You want to get it spinning like that. And what is the force you need to apply to get that torque? So the torque will be equal to force times the radius of the Earth. Okay, so the force would be torque times divided by the radius of the Earth. And 1.38 into 10 to the power 28 Newton meter, and the radius of the Earth is 6,400 kilometers. That's that many meters. Okay, so the meters will cancel and you'll get a newtons. Yeah. So the force would be, so that's 10 to the 22, and what we'll do is, that's 10 to the 22, we'll borrow one, that's 13.8 divided by that. Okay. Okay. So that's how many. Okay. So to give this and put this in perspective, the mass would be. So it would correspond, if g is the acceleration due to gravity, divide that by 10. So the mass would be 2 into 10 to the 20 kgs. And so, I mean, our masses are about 50, 60 kg, but let's say a 100 kg heavy person. So that's 2 times 10 to the 18 K people. That's 2 million billion people would have to hang on to Earth to give it that acceleration. All right.